But let's say it looks like this. So something like this. I don't know what your problem asks for specifically. Could you tell me the specifics? All right. Did you want me to do both parts, or just part B, or part A, or all of it? What do you want me to do? Okay. So let's say that what you said is true. Everything here is 65 kilograms. So if that's 65 kilograms, then can we effectively say that our free body diagram is going to look like this? Any question about that? I see two tensions acting on the box. You are part of the box system, so you are holding onto the rope. You are part of the box. And the other side of that rope is connected to the box. So there are two upwards forces. They have to be equal because they are tension. And we talked about if it's a single rope, the tension is everywhere the same inside the same rope. So two upward forces, one downward force. And in part A, that net force equals 0. So 2t minus 650 equals 0. So t has to be 325. But then you wish to move upwards. Now, by the way, this system could have been moving upwards, and it'd be the same answer. As long as the velocity is constant, I could say that he is pulling rope outwards in such a way that the system is moving up at a velocity of 2 meters per second. And it'd be the same answer. Because to move at constant velocity still requires a net force to equal 0. And so this would be the amount of tension he would have to apply to stay still, or move up at 2 meters per second, or move down at 2 meters per second. I find that students screw that up because they think somehow because they're moving, he has to be pulling harder on the rope, but he doesn't. But if he wants to accelerate, then he'll have to pull harder on the rope. And that's part B. In part B, they say that he is going to pull with 400 newtons of force. So what is the acceleration of the rope, of the box? Well, in part B, the net force no longer equals 0, it equals ma. But it's still going to be 2t minus mg equals ma. And in this case, that's going to be 2 times 400 minus 650 equals 65a. Yeah?
Why is it not like 200 per row?
Why would it be? Did we divide it up last time? The rope was 325 last time. Both ropes have to pull upwards with 650 to hold me in place. Why would me pulling down with 400 suddenly divide the tension in half on the rope? The tension has to be the same everywhere in the rope. So if I pull down with 400, then the tension I apply here provides 400 newtons of, is 400 newtons of tension. That also means there has to be 400 newtons of tension here. Okay. I think if I only provided 200 newtons of tension, I would be going down. Because I'd have total of 400 newtons upwards, 650 downwards, the acceleration would be downwards. But I think this one would be acceleration would be upwards. I get a positive acceleration too, so that makes sense because I've chosen upwards to be positive. How's that? Excellent. Let's study the idea here that let's say the pulley has no mass or negligible mass. Let's say that the pulley itself is much less massive than the person in box. Is that okay? So we can treat it like zero mass. The pulley doesn't go anywhere, does it? The net force on the pulley is zero. It would only matter if the pulley was accelerating. So it's not. So net force is zero. There are three forces acting on the pulley. There are the two downwards tensions. Just throw that anywhere. If that's a phone, shouldn't I ask you to present this problem? And there's the upwards tension, or how about we put the ceiling tension? How's that? That way I can differentiate it. Now, if the pulley had mass that was not negligible, I'd put mg downwards too. But I want to kind of prove a point. If the net force is zero, how much weight does the pulley have to support? A lot of people think that the pulley's tension is going to be 650 because the guy is 650 with the box. But it's not going to be 650. It's obviously not going to be 650. And that's because the tension on the rope attached to the ceiling is going to equal 2 times the tension in the rope, which is right now 2 times 400, which is 800 newtons. A lot of people are like, well, why? If the person only weighs 650 newtons, why is it that the force on the ceiling is 800 newtons? Well, it's simple. The guy's not just sitting there. He's accelerating upwards. So the ceiling is what's actually doing the pulling on the person. If the ceiling couldn't support this, the ceiling would fall down. It's the ceiling that pulls up on the system that causes the system, which is the guy and the pulley, to accelerate upwards. I don't expect you guys to fully understand this all the way, but it is often why people have disastrous results when doing home improvements on their own. They believe they can hang on things that they can't hang on. Well, why? It says it can hold my weight. Yes, it did, but it didn't say you could swing on it. That's different. That changes the dynamics here. It said you could hold your weight, not pull up on it. I've jumped up there and I've held this bar tons of times. Yes, but you were doing pull-ups on the bar. And every time you pulled up on the bar, you were asking the bar to hold more than your weight. You were making the bar hold the unbalanced force of you accelerating upwards. So people don't take into account. Engineers need to. You have to design systems to withstand the fact that your inertia changes as you accelerate. You are harder to move when you are trying to accelerate. So the ceiling has to pull up with more than the weight of the person in order to get them up there. That's a more interesting conversation. I'm going to ask you guys to do something else today. And this first one I'm doing purely because I think that you need, I don't know what the word is, numbers. You often don't like things without numbers, but I hate numbers. They get in the way, and they fixate you on something that's not necessary. Not to mention the fact that half of you can't use your calculators. So the moment I have numbers in there, I know I'm running into trouble. But I'm going to do this because, you guys like numbers. This is a car, I guess. There, it's a car. It's driving away from you. So that rectangle is the license plate. And these things are the tires, okay? Everybody follow along? It's a car. It's sitting on a sloped, banked road. So you guys understand what a banked road is? A road that's at an angle. All Florida roads are at some kind of angle, so the water will run off of them. Generally, roads in Florida are pitched at the middle, so the water runs off to the sides, even if it doesn't look like it's banked very much. But if you want to have people drive onto divided highways, often the on-ramps are curved. You guys have seen the knot that exists over by the airport, right? Well, look at those roads. They're not flat. They're banked. Now, the reason they're banked has to do with the fact that those cars are driving in a circular path. And the banking is there to help them. Thus, anybody who's watched any Daytona racing knows that they race on a banked oval. Now, there's a reason for all of that. Not all of it will be clear to you right now, but some of it shall be. My question for you is quite straightforward. If the coefficient of static friction between the tires and the road is 0.8, what is the maximum angle that I can bank this roadway but not have the car slide down the embankment? What's the max angle that I can pitch the road and still not have the car slide down the embankment? There's a friction problem. One that we talked about the day before yesterday. If you don't know where to begin, I think free body diagram is where you begin. I will say this. I've kind of made it pretty clear the conditions for this problem, but if you're still struggling, this has got to be a net force equals 0 problem. We don't want the car to slide. But you will only be doing this problem right if at the end you have an inequality for your answer. So I'll wait patiently, but I know that you guys can get all the way to the end of this problem without any assistance from me, because nobody has asked me any inclined plane questions in this class, which means you must understand them perfectly. I say this a lot, and I know it's gonna come back to bite me someday, but when we've done a problem, I kind of believe that you know it. Now, I understand that you are expecting me to give you 25 examples of that same question, like they happen in math class, so that you can repeat it over and over and over again, so that it's now in your memory. But I'm going to say it like this. If you know that you need to repeat something 25 times in order for it to work out in your memory, why do you need me to give you the homework that does that? You follow me? I'm not going to. We have done an inclined plane problem a couple of times. I don't see any need to keep doing it over and over again. You know if you can do it or not. Practice. I'm sure your textbook will have 20 or 30 practice questions in there. But this isn't the first time we've done an inclined plane question, is it? I don't believe so. So every time we do an inclined plane question, it's probably going to be largely the same as the last one. There are 3 forces acting on my system. They look like this: normal force, frictional force, mg. I'm going to have a coordinate system that's aligned with the ramp. It makes the most sense. Satisfies condition number 2. It's lined up with as many forces as possible. Most I can line it up with are 2. So there we go. Now, this is theta. And I have had people that are still struggling with that, but that's where theta goes. I know where the normal force is. I extend it down to the other side. And it's the angle between this part and this part. Now let's see. Break that up into its 2 components, because that is the next step, right? Take any off-axis forces and break them up into their components. Those seem like the appropriate components. And this is mg sine theta. And this is mg cosine theta. And yeah, I'm skipping some of the steps because I've done it before. It's in your notes. I don't have to do all of the steps. Maybe you do. Maybe you still have difficulty realizing that this is the opposite side, this is adjacent, and this is hypotenuse. So do more steps if you need to. But if you've done one inclined plane problem, then you understand that there's always going to be an mg sine theta down the ramp. And there's always going to be an mg cosine theta into the ramp. You could begin to internalize this a little bit. Either way, if I make down the ramp positive and up positive, then if these two equal 0, I get mg sine theta minus friction equals 0, and normal minus mg cosine theta equals 0. This is the result of an inclined plane that has friction. If it's accelerating, then probably one of these equals ma. All right. Oh, by the way, looks just like the one with the tension, right? So we've done this problem more than once. Last time it had tension there and it still equaled 0. This time it's just friction holding it in place. But friction holding it in place means something else. In this case, we know it's static friction. We know that for sure because net force equals 0. It's not sliding. That makes it sliding friction. That makes it static friction. So it seems to me that if I wanted to have an idea of the threshold, I should use the idea that I have a threshold here. I told you guys this yesterday, and or day before yesterday, I'm gonna reiterate it. If you have an inequality, you plug into the inequality. That preserves the inequality. And you should always attempt to preserve an inequality if you can. It helps you make sense of what's happening. So I want to preserve the inequality, and I will do so by noticing that F equals mg sine theta, and put that there, and N equals mg cosine theta, put that there. So that when I do, I get mg sine theta must be less than or equal to mu s mg cosine theta. Well, now I've got something. I got something I could probably use. And I know you can plug in your numbers, but I don't care about the numbers. I do know that mg is non-zero, so I can divide both sides by mg. And I can also divide both sides by cosine theta as long as cosine is non-zero, which means I can't make the bank angle 90 degrees. Okay, that's really what it says, that there's nothing that will stay on the wall if you make it a wall. I can't drive on it if I'm a car. So sine theta divided by cosine theta must be less than or equal to mu s, or tan theta must be less than or equal to mu s. If I don't want the car to slide, that's my boundary condition. Not only do I know that the actual angle, the critical angle, is when tan theta equals mu s, I know that it's all angles up to and including when tan theta equals mu s, which is why having the inequality here is more powerful than just making it equals. The only way to preserve that inequality generally is to substitute into the inequality. Yeah, you can put in the 0.8 and find the angle. You know I don't care about the number. This one's not terrible. That's not terrible. But I think you're going to like it. Well, actually, you're probably not. And we're short on time. I feel like we always are. A force is applied at an angle to a box of mass m that has a coefficient of static friction of mu s between the box and the ground. What is the minimum size of F that will just get the box moving? What is the smallest force you can apply that will get the box to start moving? If you don't know where to begin, then you don't know that this is a force problem. Because if you know it's a force problem, you know where to begin. This is a force problem. The next thing, though, is you may not know whether to make this a first law problem or a second law problem. But if we're talking about just getting the box moving, then we're talking about just having the box move at constant velocity. Anything more than that will accelerate the box. So I'd say that this must be a net force equals 0 problem. You may not think of it that way, but you need to start thinking of it that way. Again, if you don't know where to begin, free body diagram. want to wait around too long for this. So I think I'm going to start. Did you list a downward force for weight? Seemed like a good idea at the time. I think it still is. Did you list that there is an applied force suggested in the problem? Force of value F at an angle of theta. Seems like a good idea. I also think that the object is in contact with the surface, so there's bound to be a upward force that's normal. And clearly, with the introduction of mu s, that suggests that I'm going to have some frictional force. So, is this what you have? I would probably also go ahead and make my coordinate system, and I'm going to align it with the likely direction that the box moves, but more importantly, I'm going to align it in such a way that the forces all balance out. All right, like that. That way it's lined up with all sorts of forces. The only one that's not is the applied force, which I'm sure, because you guys are keeping up and are slightly ahead of me, you've broken up into its components. A horizontal component and a vertical component, which is what I would do next. So mg cosine, what am I doing? Mg f cosine theta, f sine theta. How we doing? So all the same things you did? It's not the read I get on some faces, but on others, yeah. Net force in the x direction is where I'd start. F sine theta, cosine theta, minus friction equals 0. That's the only two sideways forces. How many up and down forces do you see? I see 3. So net force in the y direction, normal, minus mg plus f sine theta, all equals 0. Pretty good, except we want f. Right? We want the size of the force. It's not spoken in here, but I doubt we're allowed to have anything but the given information in our answer, which would be like theta, m, and mu s. So it's not like I can solve this for f and say that's the answer. It'd have friction in it. Friction's probably not allowed to be in my answer. In the same way, I probably can't solve this for f and let that be my answer because I'd have normal force in it. I'm pretty sure the only way I'm going to be able to get an answer is if I only list the things that were given to me at the start of the problem. I made up n, and I made up the frictional forces, things I think are happening. So I'm pretty sure the next step is going to be to consider finding a way to deal with the friction. And I think this is the way we're going to do it. And that means subbing into this function, so I cannot have friction and normal force in my answer. That means solving this for f and writing f cosine theta must be less than or equal to mu s times, and now solving this for normal force and plugging that in for normal force, which there we go. This is a function that could be solved for the pulling force. It's not pretty, but it could be done. Now, I think you guys can do this, but I know some of you can't. At least not the first time. And some of you still don't know why we're here, but there's a lot of algebra here. I mean, I would distribute that mu s now I'd probably move the two terms that have force to the same side. factor out the f. Assuming this is non-zero, and I have no reason to believe it could be zero, I'm adding two numbers together that have to be positive. Oh, I like that. That's good algebra. Not quite the answer, but good algebra. You see, this tells me the force necessary to keep the system in place. If I want to get it moving, not only do I need to get up to the equal sign there, but I probably have to pull a little harder to get it started. Right? Our condition was that this would keep it in place. Now, I know there's a lot there, but it stopped being physics after this and started being algebra. That doesn't mean you're good at it, or that you understood all of those things, or that you thought to do that, but that's where it stopped being physics and started being algebra. By the way, I know you're packing up, and you should, but it occurs to me that none of this is true unless this is true. Do you understand why I'm writing this? I'm not even sure if I need the equal sign there, but I definitely need the less than. Because if this isn't true, the box is no longer on the table. I've pulled it off the table. I've lifted it. I've pulled with an upward force that's greater than the weight of the box. I saw that at the beginning, and you probably should look for those things. All right, that's